So today I'm going to talk about accelerating black hole imaging with Enzyme. I am a member of the Event Horizon Telescope and the next generation Event Horizon Telescope. I'll be talking about that a little bit today. This was the telescope that took the picture of the black hole a few years ago in 2019, and then another one in 2021. So I'm going to talk about some of the work I've been doing to try to accelerate our imaging pipeline with Enzyme and Julia. So I just thought I'd give a brief introduction to what a supermassive black hole is, because this is what we actually image. So a black hole, I'm sure many of you have heard about this, is a region of space-time where the pull of gravity is so strong that nothing, not even light, can escape. The boundary of this region is called the event horizon. And what we're interested in are black holes that are, astronomers are notoriously bad at coming up with names. So we come up with a name supermassive. And these are black holes that are about 100,000 times the mass of our sun, to some even approaching 10 billion times the mass of our sun. The black hole that we took the picture of the first time was about 6.5 times billion the mass of our sun. These black holes, though, have a bunch of other really interesting features. One is that we don't actually take a picture of a black hole. We take a picture of the material around the black hole. This is known as an accretion disk. This is composed of extremely hot, diffuse plasma. But because of this and because of the really fun natures of general relativity, you get a bunch of really interesting features in the image. One is, because gravity is so strong, you get these regions around the black hole called a photon sphere, and this is where light can just orbit around the black hole on an unstable orbit, but you could just have light orbiting around the black hole. Because of the existence of this photon sphere, you get this really thin ring-like image or feature in these images after you ray trace them, and these are called photon rings, and these are composed of light that's gone around the black hole maybe a half time, once, twice, three, up to infinity. The other thing that's kind of interesting is you get this inner depression that we call the inner shadow. This is actually just the footprint of the event horizon. So nothing can escape, so it just looks really black or really dark compared to the rest of the image. So how do you take a picture of a black hole? Well, turns out you need a telescope the size of the Earth. Unfortunately, I can't do this. I can't just put a telescope on Earth blocking out the entire night sky for everyone. So we have to get creative. And what we use is a technique called very long baseline interferometry. And what this does is it puts a bunch of radio dishes around the planet. Our first set of data had about 8 dishes spread all across the planet: Chile, Hawaii, Mexico, Spain, South Pole, and Arizona. And then what you do is you use computational techniques to basically link all these telescopes together, making a telescope basically the size of the Earth. And to put in perspective the resolution, so the James Webb Space Telescope, I'm sure some of you have seen the pictures. These are these big, beautiful pictures of galaxies and stuff. They have a resolution of about 10 to the 5 microarc seconds. Units don't matter. The EHT has a resolution of about 20 microarc seconds. So that's like about 10,000 times the resolution. And so this is what lets us make images that look like a black hole, that make the images here. That first one is of the galaxy M87, and the second one is Sagittarius A star, the supermassive black hole at the center of our galaxy. So what's really kind of fun and unique about the EHT, I think, compared to other telescopes, is our actual data reduction pipeline. So like I said, we have a bunch of telescopes spread across the planet. Each one of these telescopes operates basically independently and just record data, like digitally record data. And the amount of data that we actually produce from this is it's petabyte scales. So to actually get this data, we then have to put it on a plane and fly it together. So a big reason why the EHT takes so long to produce images is we have to wait half a year to get the data out of the South Pole, because the South Pole is really cold and you can't fly for about half the year. So once you get that, you fly these huge petabytes of data to these EHT correlators. There's one in MIT Haystack and there's one in Bonn, Germany. Once you get this, you correlate it together, making intermediate data product. Then you do calibration. These are the greatest people ever. They get not a lot of love, but they're really the reason we can make images. And then the very last step is the image reconstruction. And so to put this data reduction level in perspective, we start with a petabyte of data. After it goes through the correlator, we're at a terabyte, calibration a gigabyte, and then the image is about a megabyte. So this is a 10 to the 9 order reduction, and in data volume. So this is pretty unique to us, and it's kind of like what we like to say is the EHT is really a computational telescope. Every part of it along the pipeline depends on HPC or something along this. So, but what I'm going to focus on is the last part. This other stuff is really cool, but I'm just going to focus on actually how we make an image. So the first step is what we actually measure. So what we actually measure is not the on-sky image. What we measure at the telescope is just incident electric fields on each radio dish, and then we measure phase delays. It doesn't matter too much, because what really comes out of it at the end of the day is we measure, each pair of telescopes measures a single Fourier amplitude or a single Fourier component. So we're just measuring one position in the Fourier domain of this image. And this is it. So then you have a bunch of your 8 telescopes and you measure a bunch of different pairs. So you get a sparse sampling of the Fourier domain. But this is for an ideal interferometer. In reality, there's the atmosphere, messes everything up. Every astronomer knows the atmosphere is your arch nemesis. On top of that, you have the telescopes aren't perfect. Maybe they're pointed in the wrong direction. Maybe one of the cables is like a little janky, or maybe someone kicked the cable. This has actually happened, and you'll see the cable get kicked and the data go wild for a second because someone bumped it. So there's lots of things you have to take into account. So we have these things called telescope gains. Basically what it means is it just corrupts our visibilities. And so what we don't, or it corrupts our Fourier components. So what we measure are these complex visibilities or these complex numbers which are related to the Fourier components but can be scrambled pretty nastily on a per telescope basis. On top of that, once we have these Fourier samples, you have to go from this data to an image. This is really hard because, one, we have a limit on how far out in the Fourier domain we can get. This limit is set by the diameter of the Earth. So unless we go to space, this is what we have. So we don't actually see this high, precise, beautiful image. We see some fuzzy version of it just because you don't have Fourier sampling at long baselines. But because we only have 8 sites, we also have all these gaps here. So you can't actually do an inverse Fourier transform at this point. It's impossible. It's completely unconstrained. So you can't just go straight from the data to the image. It's unfeasible. So instead what we do is we do the good old opposite. We start from an image, and then we're going to start comparing it to the data. So this is in physics lingo, it's called forward modeling. In statistics, it's generative modeling. So we'll start with some image model. Now we do some computational stuff here. We do an NFFT because this tends to be the most efficient thing we do. We don't have an equal sampling in the Fourier domain. We have a sparse sampling. So these non-uniform Fourier transforms let us use FFT type algorithms, but with non-equal spacing. And Julia's actually provides a really fast version of this, which was nice for us. So once you have your Fourier components, then you have to apply all this annoying atmosphere and telescope stuff. This ends up being a sparse matrix multiplication going from your Fourier components, multiplying onto your gain stuff. And what we actually end up seeing is our data, instead of looking like this beautiful, nice curve, this is what we actually see. And so this is what we actually have to fit at the end of the day. The signal's pretty scrambled. Once you have this, then you can compare to your observed data and feed back onto your instrument model, your gains, and your image model. There are 2 approaches with the EHT for this, or at least 2 approaches that I'm comfortable with. One is regularized maximum likelihood. This is where you basically set up a cost function. You want to optimize the likelihood, so find the best part of the image. And then there are these things called regularizers where you'll fold in maybe additional assumptions, sparsity, smoothness, whatever. The other approach, this is the approach I'm a fan of, is kind of solving the Bayesian inverse problem. So you have a likelihood as well, but you also have a prior on an image, and then you try to sample and construct all possible images that are like consistent with the data. So in 2019, we had 2 main tools to look at this. There was EHT imaging. It's a Python code, really focuses on RML. And then there's Themis, which is a Bayesian C++ code. They have pretty different use cases. EHT imaging was developed for interactive desktop use. Themis was focused on distributed computing, heavily MPI-based from its origin. We are lowly astronomers. It's not that easy to get most of us to use this, so we have to put a Python post-processing thing at the end. I helped develop Themis, and I don't want to go back, but that's besides the point. They both make slightly different assumptions for what you can do. So EHT imaging. Oh, okay, it's back. EHT imaging can't self-consistently solve for these instrument gains and image. They kind of do these weird steps in between. Sometimes converges, sometimes doesn't. It's all right. Themis approximately solves for the instrument effects and then tries to solve for the image self-consistently. But both methods don't use autodiff in any way. So EHT imaging requires all gradients to be handwritten. This is a bit of a pain, and it doesn't work with complicated models that we sometimes have to deal with. And by doesn't work, I mean deriving the gradients by hand are just unwieldy, and we're mortals. The other thing is Themis doesn't have any autodiff functionality at all. I heard someone say, we all hate finite difference. Well, this used finite difference, and then it used MPI to kind of parallelize over the finite difference for these models. The downside of this is that EHT imaging and Themis both required a week of high-performance computing for the M87 results. This is really slow for the data volume we have and the data volume you will have in the future. And this was kind of unfeasible. And so, why not use autodiff? Well, I think maybe this has changed now, but 3-4 years ago, I don't think there was AD that was quite suited for us. So the EHT has a wide class of very nonlinear models. And by nonlinear models, I mean the parameters we fit that generate the images that we compare to the data. So we have things like geometric models. These are things like rings, disks, Gaussian blobs. And so computing the gradients of these in Fourier space end up being computing gradients of Bessel functions, hypergeometric, blah, blah, blah. We also have ray tracing models. So this is where you model the accretion flow around the black hole itself. And then you propagate rays to your eyes to see what the image looks like. These are really hard because the rays don't go on straight paths, they bend, and as you change the inclination of the black hole, the rays that you generate are different. And so it ends up being a big, nasty problem, and I don't think anyone has a fully differentiable ray tracing code in EHT or in these kind of ray tracing models. We also have non-parametric modeling or imaging. This is where you just kind of model the image as a rasterized grid and fit each pixel. These are like vector code, and but you need to use it with tools like NFFT. You have to have sparse matrix support, blah, blah, blah. And then you have to be able to maybe do everything at once because maybe you want to combine the best features of every model together. And so the AD you require has to be pretty feature rich. One of the surprising things I learned early on was that most AD systems that we looked at didn't have complex number support, and that was really annoying for us because we wanted to have complex number support because rewriting everything in terms of real and imaginary is annoying. We also need sparse matrix support. We need scalar vector code support, control flow. It's also pretty important to be able to have custom rules. I don't think I would have been able to get this to work without the ability to add custom rules, so I'm super excited to try the new Enzyme rules.jl interface. So eventually we'll need GPU and accelerated computing support, MPI distributed. Maybe we need it right now. It's not entirely obvious. So to try to answer some of these questions, I kind of spent the last 2 years kind of developing this Julia code to explore whether we can use Julia and its autodiff functionality to try to solve some of these problems, make it easier. It's already been used within the EHT. It was used in the images of Sagittarius A star, so I think it's been well received, and there's been a lot of momentum at SAO, or the Harvard Center for Astrophysics, lately to use it more and more in the EHT analysis. We also try to be very generic about the images and the corruption models we consider, and so because of this generic nature, we need autodiff. I am one person. I can't implement the gradients for every model under the sun. But because of this, because we have fast autodiff, we have all of these models implemented in Comrade or something quite similar. So the optimizations we tried to do in Comrade compared to maybe EHT imaging and Themis, one, when I need to compute numerical Fourier transforms. I use NFFT, it just scales better. We use sparse matrix stuff, again, to play the gains. This is the first code that I think that does this. It helped a lot. We'll reuse memory buffers as much as we can. Zygote is the thorn in my side and doesn't let me do this very often, so I work around it the best I can. I use and so to kind of get around this, I use like a mixed AD system. So I zygote and chain rules, and by zygote I mean zygote as little as I can and chain rules when I need to. Forward diff for certain broadcasting operations, and when the number of parameters we're fitting is small, and then I've deployed Enzyme when I was like, I don't know how to do this. Let's just see if Enzyme can do it, and it did, and it was pretty good. So micro benchmarks, just looking at a small number of parameters. So this is not Enzyme, but this is using Julia's forward diff mode. We could see that even just evaluating the likelihood, so like kind of evaluating the forward pass, I've got a 2x speed up on Themis. This was surprising to me, actually. I think it's just more optimized Bessel functions, or I've done a better job of not getting hit by like virtual function calls or something. I'm not too sure. But compared to EHT imaging, order of magnitude faster. When we get to the gradients, this is where AutoDiff really shines. EHT imaging, I think there's some massive Python overhead or something going into it. They have handwritten gradients, but it's awful, the performance. Themis is awful because it's using finite diff. It gets better as you throw 16 cores at it, but you know, it's cheating. But one of the fun things for me, and one of the things that really made me excited, was when I deployed Enzyme on some of the imaging and so like non-parametric rasterized imaging model. And so in this, I got to a choke point pretty quickly where I was trying to use Turing and some of its handwritten rules for some of its priors it had done, and one of them was scaling really, really poorly. You can see it by these blue dotted lines here. And one, it shouldn't. So I first tried to just figure out what the gradients were. I spent maybe longer than I should have, and then gave up and said, well, I can make this non-allocating. Let's just see if Enzyme can do it. And I applied it, and Enzyme basically did as well as I think I probably could have by handwriting gradients. And this allowed it to scale our models from like 10 by 10 image or a 10 by 10 raster up to hundreds hundreds of pixels at this point. So I think this was a pretty happy moment for me. It said Enzyme happy. And so now, you know, the one thing is that I still am a factor of, it's maybe not the greatest. I'm still like 10 times slower than the forward pass. This is zygote overhead, so I need to prune zygote as much as I can, but baby steps. However, already with this, I had way improved results compared to EHT imaging and Themis. So these are some scaling plots here. The Comrade blue and orange points are just whether I simultaneously fit the instrument or these like telescope corruptions and the image model together, or just the image model. But what you should really be focusing here is that Themis on the forward pass scales terribly. This is because of it uses a direct Fourier transform instead of the NFFT. So this scales as like n to the 4 or n squared for the number of pixels, not the other one. EHT imaging just has massive Python overhead, so RIP. Themis on the gradients, you can see it's really struggling again. Finite difference, RIP. EHT imaging does pretty well here because the gradients are really, really, really simple. So, but we still win here by a bit. So this was pretty good. The really exciting thing was when we compared this to like the Themis Bayesian thing. So for 2017 data, the EHT tool, Themis took about a day to a week on a cluster, depending on initialization and the number of pixels you fit. This was dropped down to about an hour on a single CPU on my laptop with basically equivalent images. So what this means is that if you want, you can check out my GitHub, the docs, and you can make some black hole images of yourself from the actual data. So that's kind of fun. It made me smile. The other really exciting thing about this is that we can apply it to the next generation of Horizon telescope. So this is where we add about 5 new sites around the planet. Or 10 new sites actually compared to like 2017. And so what this means is hypothetically we can turn this fuzzy image of M87 in 2017, this is in log scale, to this really nice sharp thing with NGEHT. And I think this Julia code is really the only thing in town that actually is able to do this other than resolve the nifty guys. Those guys are pretty good too. They can do this. The other really exciting thing about this is that we've recently expanded it to deal with polarization. We actually measured polarized light. And so using this, you can, this is fresh off the press, i.e. this morning. And what this suggests is that we may actually be able to detect something called frame dragging. So there's this region close to the black hole called the ergosphere. And inside this region, so first step back, black holes have angular momentum. They'll actually spin. So most black holes in the universe will actually spin with some velocity. Inside the ergosphere, gravity is dragged so much by the black hole that everything has to rotate with the black hole. Nothing can rotate against the black hole. As soon as you enter the ergosphere, you'd get whipped around and have to actually rotate with the black hole. And what this kind of shows is that with the NGEHT, you might actually be able to detect this like counter spinning. So this point where gravity becomes so strong that the plasma has to start rotating with the black hole, even if initially it was counter rotating. So I think the next steps for me are to integrate more and more of Enzyme into Comrade. I've been really impressed with just the performance I get out of the box without having to write chain rules or like reverse rules or forward rules. I'm going to try to do this to lower some of that gradient overhead. Some of the things that were preventing me from doing this originally were, this has been fixed a lot lately. It just didn't work with the Julia runtime a lot. So if I allocated in the code, it would segfault. That's shockingly been fixed, amazingly enough. Every time I try it, it seems to be better. So I'm really excited. And then I also need a rules system. I don't think I want to AD through an NFFT or FFT. And there's other operations, as I just learned, that I also don't want to AD through. So maybe some more rules will help me with this too. I know I'm the coder at this point, so I know. Well, maybe I don't know. That may be pretty scared. So, but that's kind of like the next steps for me. So, yeah, that's about it.
Thank you. Any questions?
No worries. I don't have a question regarding Nifty. I was looking at those black holes from the competitors. No, the one before that. Yes, the left picture looks a bit box-like. Where exactly does this come from?
A very low dimensional raster and then rotate it, and you are literally seeing the boxes of the pixels.
Okay, I see. That makes sense.
You remember when I said Themis uses finite difference? If you go up beyond 5 by squares quadratically, and with finite difference, this gets bad really fast. So this is.
Other questions? Comments? Somebody wants to get into astrophysics now?
Yes. Hey, we are actually hiring. I was told to poach some people here to work on this with us. So.
Okay, then let's thank Paul again.